Thanks everybody for coming. My name is Rafael Busso. I'm probably the most foreign object in this room. I work on quantum gravity and cosmology over in the physics department. And I want to welcome you to this mini workshop on quantum information, space-time, and tensor networks. Let me just say one or two words about the history of this workshop. There's sort of a large-scale and a small-scale reason for it. The large-scale reason is that, certainly from my perspective, I perceive that techniques in condensed matter and quantum information have, well, it'd be an understatement to say that they've played an increasing role in recent years in my field. I would say they've been central to revolutionizing my field, and it seems clear now that those of us who are interested in understanding how space-time works, how quantum gravity works, are going to need to learn the techniques that you guys have developed in these other fields. And tensor networks are one prominent example. Notions from quantum information, such as the properties of entanglement, entropy, are another. And if we knew exactly what we need, we wouldn't have needed this workshop. The idea is to teach each other some of these techniques that we vaguely feel are relevant, and to teach each other the problems that we care about. A lot of you might have the solution to something that you don't even know is a problem, and that was that was one of the goals. On a smaller scale, you're all participating in arranging a marriage. It's not monogamous, unlike entanglement entropy, but I hope it works out anyway. So I'm hoping that the groups that are here represented by Umesh and Joel and myself will in the future find ways to interact more with each other. And we're really also just trying to teach each other our respective fields. And I think Berkeley is in a very good position to take advantage of the expertise that's here. So thank you all for coming and helping us with that. And I look forward to learning a lot today. And the talks again today are really aimed not necessarily sort of primarily as presenting research results and cutting edge stuff, but as being pedagogical. There's a lot of time for discussion, and no question is too naive. So I'd like to invite Patrick to start. He's one of the people who've really pioneered breaking through the barriers between these fields, and he will talk about space-time entropy and quantum information.
All right. I like that you had to actually read my title, even though you're the one who assigned the title. So I'm going to try to be pedagogical. The intention is to try to illustrate some of the connections between space-time entropy and quantum information. I am going to present some work with Bartek Czech, Brian Swingle, both of whom are here, and Nima Lashkari, but in the context of trying to present a larger set of questions, and then the talk is going to trail off towards the end and just be a list of questions, hopefully prompting discussion with the rest of you. So just to set the context for the computer scientists, one of the major questions that we're interested in here is the relationship between entanglement and the structure of space-time. And there's a setting in which, let's call it a toy example, in which we can actually examine some of those questions. And that's called the anti-de Sitter space conformal field theory correspondence. So this is a theory of quantum gravity in a particular setting. So it's a theory of quantum gravity. So we can picture it as sort of a universe in a bottle. So say D plus 2 dimensional theory, there's a gravitational theory, but asymptotically this space is anti-de Sitter space, which means asymptotically it's the maximally symmetric negatively curved space-time. And you can put stuff in the model deep inside if you want, and see what happens. Now what's interesting in this context, or this for this theory of quantum gravity, is that it is thought, and there's a great deal of evidence to supporting this conjecture, that the theory of quantum gravity is precisely equivalent to a standard quantum field theory, so say just a theory of qubits living on the boundary of this space-time. So as I said, this is a space-time that's kind of in a bottle. Someone who's inside can send a signal, shine a light towards the boundary, you'll get to the signal will get to the boundary and come back in finite time. But you can place this quantum field theory living on the boundary, again, a theory of qubits. The boundary has one fewer spatial dimensions. And all questions that you would want to ask about quantum gravity in principle can be asked in the boundary theory. The boundary theory doesn't have gravity, so it eliminates a lot of the complications of thinking about a gravitational theory, or maybe it's just a standard quantum theory. So this is in particular a context in which we see something kind of miraculous occurring, which is the emergence of one direction of space, right? The radial direction of space isn't present in the boundary theory, but it somehow is present in the bulk theory. And so the analogy that is often given in this context is Plato's cave. You know, to think back to this story that Plato gave, someone lives in a cave. All he sees is the projections on the wall of the cave of something that's happening outside. And if you try to, you can imagine if you were in this situation, you tried to construct a theory of the shadows, this would be a very nonsensical theory, that the shadows themselves don't have enough information to predict their own future behavior. But in this context, really quite miraculously, the shadows being, of course, the play of what's happening on the boundary, there's enough information there to predict the future behavior. And on top of that, not only is there enough information, but those shadows behave according to the rules of some local physics, right? Which is really quite a miracle. Yeah, it's something of a miracle. So again, just zooming in, we're going to be speaking mostly about space rather than space-time. So the spatial slice of anti-de Sitter is hyperbolic space. And so the metric is, in this rendition, the fish counting metric. The distance between A and B is the smallest number of fish you have to pass through to get from A to B. It's negatively curved, so the sum of the interior angles of a triangle is less than 180 degrees. Much of what I'm going to say, I'm going to sort of be focusing on the two-dimensional case, or two-dimensional space. Some of it generalizes, some of it does not, and that's one of the questions that we're interested in, is the extent to which some of these ideas generalize. Now, as I said, you can put stuff inside your space-time. So for example, you could drop a black hole deep inside ADS and ask what happens. Now, that's going to distort the geometry, and so your geodesics are no longer going to be just the curves that I've drawn here. They might look something more like this. And if you want, you can write down the metric, but we're not going to focus on that for the moment. Now, this connection, there's this idea that there's a connection between entanglement and the structure of space. So where did that idea come from? And that actually, I'd say, first originated by thinking about a particular example, the two-sided ADS black hole. And this is what's called a Penrose diagram. And it's a way of thinking about the causal structure of a given space-time. And so in this diagram, it's drawn such that light rays propagate at 45 degrees, like I've drawn here. And so if I think about being at this point in the space-time, time is, say, in the vertical direction, and I shine a light ray out that way, it's going to hit the boundary, which is this vertical line. And each point in the diagram has, say, a two-dimensional sphere attached to it. And so this vertical line here represents the boundary, and there's a conformal field theory living on that boundary. On the other hand, I can also shine rays in this way, and the horizontal direction, I should say, is the radial direction in this space-time. And move to this region. And if I'm in this region of the space-time, as you can see, any light rays that I shoot out eventually are going to hit this singularity. And so this is the interior of the black hole, this wedge up top. And this piece outside, the wedge, the sideways triangle, is the exterior of the black hole. But if you look at the picture, there's another region on the left, which looks very much like the region, on the right. And so this black hole actually has two exterior regions. And so each exterior region looks like some space-time. There's a black hole in it. But if you were to jump into the black hole, that interior is shared between the two space-times. And that's how they're linked together. And so you can think of it as the interior of the black hole forming a non-traversable wormhole between these two exterior regions. Just to draw the picture, if I think about this spatial slice here, it has a shape that looks somewhat like this, sort of abstractly. Now, as we said before, there's a conformal field theory associated with each boundary in the space-time, and so there's a quantum state living on that conformal field theory. In this particular case, because we have two boundaries, there are two conformal field theories, and we can ask what is the quantum state associated with this particular geometry. And the quantum state associated with this particular geometry has a very interesting form. It's an entangled state between left and right. And it's entangled in a very particular way. There's actually a Hamiltonian associated with the system. It's the sum of two independent parts, one for the left, one for the right. There's no interaction between them. And so we just have a state which is, this is the Schmidt basis. And it looks like the purification of a thermal state. Right? So if we were to trace over left and think about the state on the right, this would be a thermal density operator. And so the thermal density operator in the conformal field theory corresponds to a black hole geometry. But the fact that the two exteriors are linked through the wormhole corresponds in this, manifests itself in this context in the state being an entangled state between the two conformal field theories. And so this generated the idea, which was, I guess, elaborated by several people over time, that the entanglement between the two conformal field theories generates or links them together through this link of space, this wormhole. Now, I guess one should also say that one can construct geometries, one-sided black hole geometries, in which there is no wormhole, and then confirm that the lack of entanglement corresponds to the lack of some kind of bridge connecting them. So this idea, I should say, was initially observed in this example. And yes, Wim?
Just to understand this picture a little bit better for loop liking. The boundaries are like the left and the right side of the square that you have there?
What are the boundaries? Yeah. What are, like these boundaries right here?
Yeah.
So each boundary, like in this external picture, let's go back to this picture here. Each of them, at each point in time, is one of these spheres, right? Maybe the picture going back a bit further. Each of the space-times looks like this, but there's a black hole in it. So you sort of have two bottles like this, but inside the black hole, they're linked together. That is the way to think about it. Does that make sense?
But it is the red side of the square.
It is the right side, thank you.
Can you also just say again that state that you have at the end of the slide? This is a state you're saying exists, could exist, or actually describes the state of the two boundaries?
The status of this state here?
Right.
So I'm not an expert on how one does these calculations, but I think that there's a great deal of confidence, and there are people in the room who know much more about how one does the calculations, that in the ADS-CFT correspondence, there's a good justification for this being the correct quantum state that describes this particular geometry.
So it's a joint quantum state that describes the two boundaries.
Sorry?
It is the joint state that describes the two boundaries.
Yes, exactly. Yeah. Okay, so the question, right, and this is not a question that will be resolved today, but a question for discussion then, is how far can you generalize this example? Does space actually emerge from entanglement itself of some amorphous, non-geometrically organized degrees of freedom? And some strong evidence in that direction some further evidence in that direction was found by thinking about entanglement in conformal field theories that have these gravity duals. And that was actually, we'll get there, but work by Ryu and Takinagi, and Shinsei Ryu is in the audience somewhere, I think. So the situation there is that you have a conformal field theory again, so just think of it as a bunch of qubits, and in this case, say, organized in a ring, and you want to calculate the entanglement entropy. So there's a reduced density operator for some region on the ring. The formula is minus trace of rho log rho for the density operator. And so the entanglement entropy, if you have a pure state of the ring, is of course just the amount of entanglement between A and A complement. And the remarkable formula proposed by Ryu and Takinagi is that if you want to evaluate this entanglement entropy, which a priori involves finding the density operator, diagonalizing the density operator, calculating this function, there's a very simple, beautiful geometrical way to do it in the holographic dual. And what you do is you calculate the area of some minimal surface associated with A. And the surface that you look at in this simple example, you think about surfaces that begin and end on the endpoints of the interval A and have minimal length in the bulk geometry. Now, if you remember the fish counting metric, there are many more fish out near the boundary than there are in the middle. And so this this geodesic is going to not hug the boundary, it's going to penetrate into the bulk. And so that's going to, that's actually how you calculate the entanglement entropy. Now the technical definition is that you think about surfaces in the bulk that are homologous to this boundary region A, so that they are the common boundary of some region in the bulk. And that's important sometimes, rather than this being deformed, or rather than deforming A into the bulk. So this formula generalizes the well-known and long-standing or beautiful formula for black hole entropy. That in that context, if you remember, the black hole corresponded to a thermal state of the boundary theory. And so if we wanted to find the entropy of the black hole, we could ask, well, what is the entropy of the whole boundary? And in this case, the rule is going to allow this surface to contract into the bulk, and the minimal surface is going to wrap around the horizon of the black hole and calculate the area of the horizon. So this was originally proposed based on numerical agreement that Ryu and Takiyanagi had some particular examples where they could calculate the left side and the right side and see that they agreed. And then additional evidence was found. At this point, I think there's a pretty good explanation and confidence that the formula is correct to leading order in these theories. So that leaves for an information theorist like myself, that leaves the question of how we would actually interpret this boundary entropy. What does it really mean in terms of the bulk theory? Can we actually learn something? How far can we push it in order to get a better sense of the relationship between entanglement structure in the boundary theory and geometry in the bulk? Because I guess I should emphasize that what's remarkable about the formula is it translates directly, quantitatively, entanglement, right, in the boundary theory in the form of entanglement entropy into a purely geometrical quantity in the bulk theory, right, relating these two things together. And if our goal is to understand whether space-time or space emerges from entanglement, this seems like a great starting point. So the information theoretic interpretation of entropy is the minimum compression rate, or even, well, let's say the minimum compression rate, but the minimal number of qubits required to encode the quantum information associated with that region. So if our Alice was external to this ring, right, you can imagine that this ring now is just a ring of some exotic material that Alice has in her own laboratory, and then she's going to look at the A part and try to compress that down to the minimal number of qubits while maintaining all of the correlations with A complement. The minimal number of qubits required is the entropy under some assumptions. Now, there's a sort of interesting coincidence happening here, right? Which is that entropy is the minimum over all compression procedures of the cost. But in the Ryu-Takiyanagi formula, the entropy is the minimum over all curves of the length of the curve. So wouldn't it be great and interesting, and a further development of this relationship between geometry and entanglement, if there was a sense in which every curve corresponded to some way to compress the quantum information, subject to some restrictions determined by the geometry of the curve. And that turns out to be true, in a certain sense. So to make that true, we have to alter a little bit our notion of what we mean by compressing, at least provisionally, just by virtue of the fact that this is all we can prove at this point or understand. And so if Alice wanted to compress her qubits to send them to Bob, another thing she could do is she could first compress them and then teleport them to Bob, right? And the number of bell pairs required to teleport would be the number of qubits she'd originally compressed to. And so a sort of an equivalent way of saying the same thing is that the minimal number of bell pairs required to teleport the A region from Alice to Bob is given by the entropy. And this is the statement. It's equivalent in this context, but not necessarily equivalent in general, that we're going to elaborate on. So what is the rough architecture of the bulk? There's sort of an idea that developed over time, and we're going to try to understand this geodesic sort of in little incremental bits. And the idea is that the pieces near the boundary are going to correspond to small-scale correlations in the boundary theory. In the physics jargon, ultraviolet correlations. And so here we have perhaps two sources of information that are correlated within some small community, of interest to some small community. And near the center, you have correlations on a larger scale. All right, so there might sort of information that might be of interest broadly to a much larger community. And the type of compression procedure that is going to be relevant is a streaming compression procedure. So I'd just like to give you an analogy in a very concrete context in which many of us have encountered it before. And so this is Netflix, right? If you use your laptop, you want to watch a movie. If Netflix wanted to minimize the number of bits that they were going to send you in total, then what they would do is they'd compress the whole movie at once on their side and they'd send it to you, right? And if they do that, that would exploit both what we'd think of as the UV correlation, right? The correlations that are local in time in the movie. So here's some stills from Interstellar, I guess, exhibiting ultraviolet correlation. This is a movie, by the way, in which solving the problems of quantum gravity turned out to solve or prevent humanity from total destruction. And so it's really great for the ego of somebody who's interested in quantum gravity. But this compression of the whole movie at once will also be able to make maximum and complete use of the infrared correlations, right? The correlations that are over long time intervals in the movie. And so, for example, the star Matthew McConaughey, his face, is the same face, at each point in the movie, modulo, being happy or scared. And so that type of correlation could be used in this context. Now, that's not what Netflix actually does, because when you hit play on a movie, they want to be able to display the movie to you in real time right away. And as a result, they have to sacrifice on the infrared correlations, right? They can only make use of short-time correlations and not long-time correlations. And that's sort of the nature of a streaming compression protocol. The longer a window you have access to, or the larger window, the better you can compress. And if you only have access to the ultraviolet information, then you're going to have to pay an additional cost. So what does that have to do with holography? Well, Vijay Balasubramanian, Bartek, and collaborators back in 2013 found a way, or observed that you could map a general curve in the bulk to a sequence of boundary intervals in the following fashion. So here my boundary is supposed to be this horizontal line here. So that's the spatial part of the boundary. And then I have a curve, this piece, that penetrates into the bulk. And at each point on that bulk curve, I can construct the tangent geodesic. And the geodesics, if you remember, sort of, well, in this case, they're actually semicircles. And so they will intersect the boundary at 2 points. And so each tangent, for each point on the boundary theory, we have a tangent geodesic. It will intersect the boundary at 2 points. And so that defines an interval in the boundary. And so the curve can be translated into a sequence of intervals on the boundary, like I've drawn here. So here's the sequence of intervals. And we could use that sequence of intervals to define or to constrain a streaming compression protocol. That we could have Alice, who's trying to send the contents of the interval, the quantum information of the boundary theory, to Bob. But she's going to have to do it in a sequence of steps, one for each interval. And at each one of those steps, she only has access to the part of the boundary defined by the interval. So I've drawn her large here, but she would start off only having access to this very small interval, and she could do whatever she wants. And we're going to allow her to use up bell pairs with Bob, right? So it's like teleportation. We'll count the number of bell pairs. And Bob is similarly constrained. He's going to have a sort of replica system of Alice's, and he's allowed to act on his set of qubits that are localized in space in the same way that Alice's are at each step. And so Alice will sort of move through the boundary interval. I didn't know how to make the animation to show the size of her interval changing as a function of time. But she starts off only having access to the very small bit. It grows and grows and grows in scale. At some point, she has to start moving to the right. And the interval eventually shrinks down to nothing again. And so we could ask, in this context, if Alice is trying to communicate her state to Bob using the fewest number of bell pairs possible, how many bell pairs are required? And what you can show is that the length of this curve is the minimal entanglement, the minimal number of bell pairs required for Alice to transfer the subtended portion of the boundary state to Bob using a streaming teleportation protocol with curve-dependent locality and scale constraints. And so the geometry of the bulk is translated into information theoretic structure in the boundary, and constraints on the way that Alice can access the boundary create reflect the metric structure of the bulk. Now there are two parts to proving this kind of result, and I think I'll tell you something about why it's true, or why Alice can actually do this. But one has to both show that it's possible for Alice to do this, and one has to show that there's no way to do it with fewer qubits, right? That if you really want to have an interpretation as the minimal cost, you have to not only show that there's a way to achieve that cost, but you have to show there's no way to do better. So I'm not going to tell you much at all about why it's the best possible, but I just want to emphasize that that is also something that's known. And just to illustrate, right? So here we have a curve which stays close to the boundary, and as a result, the intervals defined by the curve are all very short, right? And so this is a streaming compression protocol in which you only have access to the ultraviolet information, and so the length of the curve is large. And if you remember, the number of fish out near the boundary is very high, so a curve that stays near the boundary has a high cost. Conversely, if you allow the curve to penetrate into the bulk, you have access to more of the infrared information. You can let it go further and further and further into the bulk, and at some point, you find the length of the minimal curve. So that's the cost of a compression protocol with no constraints at all. So why is this true? I'm just going to, in the pedagogical spirit, I'll tell you about how Bartek et al. Made sense of the length of an arbitrary curve. Yeah.
You probably said this already, but the state that Alice is trying to teleport to the bulk, this is a pure state, or it's a mixed state of the
Let's say it's a pure state of the full ring, and she's trying to send a portion. So it could also be that it's a mixed state of the ring purified by some other system. So it's that all of the correlations of A with the rest of the world have to be preserved.
between A and B in the first place.
Well, let's say A and A complement, right? Like it's the usual definition if you want to talk about quantum compression, right? So there's a density operator on A, and this procedure should work for all possible purifications of A. Yeah.
Could you tell us the precise model in which that theorem is proved? What the boundary field theory is?
Oh, yeah. So for this to be true, so I guess there's an important constraint which I didn't get into, which is that entropies are generally not the answers to like if I ask the question, what is the minimal number of qubits required to compress some state? The von Neumann entropy is usually not the answer, right? That it's usually just abstractly, it's the log of the dimension of the portion of Hilbert space that you need. And only when some law of large numbers comes into effect does the von Neumann entropy become the right answer. So in this context, so this result works. We've proven only for a boundary that has one spatial dimension, and you have to have it's in the limit that the central charge of the CFT goes to infinity. Because what you really need for it to work is that at every discretized step of the procedure, the entropy has to be large. And in conformal field theories, at least in 1+1 dimension like this, you can prove that the von Neumann entropy and this compression cost are essentially the same, or the corrections go as the square root of the entropy. And so to get the leading order correction, you need the entropy to be large. Yeah.
But, for more general case, this also gives you a bound, right, for the number of
yeah, so more generally what you can, I'll tell you a little bit about why it's true, but you can replace these entropies by their one-shot versions, and then you can prove a result. But then there's going to be a gap, what you can prove is optimal, or sort of what you can prove is required will not match what you can prove is achievable. There'll be some separation between them. Yeah.
Is there a trade-off between the rate of compression and the length of this blue window?
Sorry, can you say that again?
So the rate of compression should somehow depend on the length of the blue Alice.
Yes, exactly. Yep.
And is that known, or is it behavior known?
Well, that really is the content of the result. I think maybe my picture here is a little bit misleading. That the length of the blue window is actually varying as Alice moves from left to right. That the length of the window is actually given by the lengths of these intervals that I've drawn below. And so if the intervals become long, then the compression protocol can be more effective. And the relationship is precisely that the cost of the compression protocol for a given collection of window sizes is the length of the curve. Okay, so and that's illustrated here, right? So if you have a curve where the window sizes are small, then the length of the curve is long. Whereas if you allow yourself longer intervals, the length of the curve becomes smaller until it's at its minimal size. So why is this true? This starts from a story, as I said, of Bartek and collaborators back in 2013. The Ryuta-Kiyanagi formula allows you to make sense of the length of a geodesic, but doesn't tell you anything about the length of an arbitrary curve. And so they came up with a way of a formula for the length of an arbitrary curve. So here's a curve. It doesn't actually start and end on the boundary, but in the bulk, my curve gamma. And just to illustrate, I've taken this picture from Rob Myers. How would you go about expressing it in terms of boundary quantities? So what you could do is you could say, well, let's draw tangent geodesics to that curve, like we were talking about before. So the tangent geodesics are these blue lines that become red and then blue again. And as you can see, if you draw a bunch of these things, then their kind of outer envelope is going to approximate the length of the curve. And so you could say, all right, well, let's try to add up the lengths of those geodesics that we've drawn. And if we do that, well, we get this outer envelope, but we also get these blue parts that we don't like. All right, so you have to try to correct for the blue parts. And so for each of the blue-red geodesics, that's associated with an interval on the boundary, my I1, then I2, then I3. And you could at least try to correct by saying, well, I want to subtract off these legs, these blue legs. And I could think about the geodesic that starts at one end of the leg, at the leg of one interval and ends at the leg of the other, right? So that's corresponding to the interval, which is the overlap of two consecutive intervals. And it doesn't look like it's a great approximation in this picture, but you should again remember that most of the fish are out at the boundary, right? And so just subtracting off the greens is going to do a pretty good job of approximating the length of the curve gamma. And as you take the limit where the shift between the intervals becomes infinitesimal, this actually becomes an exact formula. And so I'm just writing this schematically as the infinite sum of the entropy associated with the kth interval, this one here, minus the entropy associated with the intersection of the kth and the k minus first, kth minus 1, right here. So that's the green piece. And this is the formula for the length of a curve, a general curve, and they call this the differential entropy. So differential because, as you can see, this is really an integral of some kind of derivative, but we'll just write it in this finite language. So does this mean anything in information theory? So we are behind.
Start getting into the discussion.
Should I?
Well,
yeah, I can just. I think that sets the stage. I guess we started a little bit late, but I don't care how far I go. So
we're at 30 minutes of the talk right now, roughly.
Yeah.
So if we want to leave 15 for discussion.
Okay. So let me just take a quick look. I'll just say one thing about why it's true, and then we'll get to the discussion. So how do we connect Bartek et al.'s observation to the protocol that I was just describing? And so if we have some physical space, so now this is a two-dimensional physical space with two subregions, A and B, then we can think about the various entropic quantities associated to A and B. So there's an entropy of A, which we've talked about before. There's an entropy of B. There's an entropy of the joint density operator AB, and we can combine them in various ways. And one way you can combine them is a quantity called the conditional entropy of A given B, where you take the joint entropy of A and B and you subtract off the entropy of B. So that in this Venn diagram picture corresponds to the left-hand Pac-Man, right? You're probably more familiar with the mutual information, which is the overlap, but the conditional entropy is interesting. And in classical information theory, it really is the average entropy of the conditional distributions. It's the uncertainty about A when you know B. In quantum mechanics, something strange happens, that if you just think about a Bell pair, for example, the joint entropy of that Bell pair is 0 because it's a pure state. Whereas if you look at the reduced density operator, it's maximally mixed, its entropy is 1, and so the conditional entropy is negative. And so you would think, well, this interpretation of conditional entropy as an uncertainty about A when I know B is just nonsensical. And this fact that the conditional entropy could be negative was observed back in the 1950s, and mathematical physicists said, well, that means conditional entropy in quantum mechanics doesn't mean anything. It doesn't have any good interpretation. Because it seems like it would require you to be more than certain, which is just a nonsensical statement. Well, it actually does mean something. And what it means was written about in what is far and away my favorite, my popular science news article with my favorite title of all time. Scientist knows less than nothing. And so it was these three guys, Hordetsky, Oppenheim, and Winter, who figured out what negative conditional entropy means and just conditional entropy in general. And the answer is that the conditional entropy of A given B is the number of Bell pairs required to teleport A to B in some sense when B is already present at the destination. And that makes sense even when the conditional entropy is negative, and in that case the cost in Bell pairs is 0, and the process actually generates Bell pairs that they could use in a future round of the protocol. And that's the process of entanglement distillation. And so I won't belabor the point because we should get to our discussion. But this quantity is really a conditional entropy in disguise. And so once you realize that, you can just use this protocol of Hordetsky, Oppenheim, and Winter in sequence, adding up a bunch of conditional entropy terms and incrementally sending the state from Alice to Bob. And you get the formula that we were talking about. And now we'll get to the discussion. Well, maybe I asked the questions. So what I just told you about establishes some very interesting link between the space of curves in the bulk and the ways that you can compress quantum mechanical information. And what we're really interested in is whether space can emerge from entanglement itself. And I'd say that this result is some kind of hint that this should be possible, a hint that something more general and more powerful should be true. And do I want? Well, I don't know if I want to explain the slide just because it sets up the discussion. But I don't want to anger.
Sure, that should be mentioned. So why don't you?
Okay, so I'll mention this. What I just told you about, we can see it as evidence that something more general and more powerful should be true. And this goes back to an observation of Vidal's back in 2007, that if you have a conformal field theory, there's an efficient way to approximately represent the ground state of that theory, this conformal, this scale invariant state. And the way you do it is you represent that state as the contraction of a bunch of small tensors. And the tensors are organized in this scale invariant fashion that I've drawn on the right. So each little dot is a tensor, so it's some collection, multi-dimensional matrix of numbers. If there are 3 lengths, it's a 3-dimensional matrix. If there are 4 edges coming out of a vertex, it's a 4-dimensional matrix. And you just contract them all together, and that gives you a representation of the set of amplitudes in some basis for the ground state. Brian Swingle, who's in the room, noticed at some point that this network looked a lot like hyperbolic, like some discretized version of hyperbolic space. That if you wanted to count determine the distance from A to B, you could count the minimal number of links you had to cut to go from A to B through the graph, and that looked a lot like the fish counting metric on the previous slide. So, and moreover, when these networks are constructed, they form some way of compressing the boundary state into what looks kind of like the bulk. And that's sort of just a pictorial connection between these tensor networks. This particular one is called the multi-scale entanglement renormalization ansatz, and hyperbolic space. And one of the things that we'd like to do in this business is put legs onto this tensor network picture, really show that the tensor network can be constructed, and that the length of this curve would be the sum of the entropies of the lengths in the network. So what we need from quantum information theory, one of the things we need is to find a way to actually perform this compression in a canonical way. And there's a question, is that possible? Yeah, I don't know. Well, that's a question. We can discuss it. I'm not going to try to tell you about it. And then there are other questions that I just thought I'd try to lay out there for discussion. And we can go through them in turn, but I'll just tell you, some of the things that I thought were worth trying to think about. So what kinds of conditions on this boundary state are necessary for a consistent geometry to emerge in this sort of picture? If this picture is right, if we can actually identify the tensor network, at least in some coarse-grained way, with the geometry, what does that teach us, right? Does it answer any questions that the physicists would actually like answered, or is that just sort of a mathematical curiosity? Does this picture answer, or what types of things are missing from this picture? There are reasons to think that it's hard to use it to look at the geometry at sufficiently fine-grained scales. And it's also totally static, right? We're just talking about space. We don't know anything about the dynamics of these tensor networks. And that sort of brings us into another question. This is all about space. And if entanglement is supposed to stitch space together, what stitches time together? Is there some notion of entanglement in time? Or what are the appropriate information theoretic quantities to discuss in that context? I think actually some of the computer scientists here may have things to say about that. I'll just toss out the word history, state, possibly being relevant. And then maybe we'll leave this for Steve Schenker and others, the last line. So those are questions that I'm hoping people in the audience will have something to say about. And maybe we should just take them in turn.
Patrick,
Yeah.
I think maybe this would be a good place to stop so that we have time for at least a couple of questions.
Oh yeah, no, that was my idea.
Oh, okay, good.
Yeah, I'm not going to say anything. This is just this is the audience participation section. You can actually address any of the questions or anything else, or ask me a question. But the idea is that now we're supposed to set up a discussion. So yeah.
Yeah, maybe we can go back to where we can see all the questions.
Oh yeah, sure.
Oops. People can ask about it. Yeah. I can't answer any of them.
Yeah. If you can answer any of these questions, that's great. But you can also just ask further questions. Questions beget questions.